Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are taking a deep dive into magnetism and Gauss's law from Unit 5, Magnetism and Matter. We promise a straightforward, very conceptually rich explanation that will clarify this foundational pillar of electromagnetism and really help you master the physics behind it. So, let us start with a simple, everyday puzzle. We have all used a magnetic compass, right?
Yes, of course.
And we know the compass needle's north-seeking tip. It reliably points towards Earth's geographic North Pole. Now, you also know the most fundamental law of magnetism: opposite poles attract.
Right, opposites attract.
So think about it. If the north tip of the compass needle is being attracted, what kind of magnetic pole must be sitting up there near the geographic north?
Okay, wait. If opposite poles attract and the north tip of my compass is pointing north, then Earth's geographic north must have a south magnetic pole. Is that right? That feels backwards.
You got it. It feels backwards, but you are absolutely correct. And here's the surprising thing. That's exactly how it is. Earth's magnetic field is actually oriented so that the planet's south magnetic pole is located very near the geographic North Pole.
That is so confusing. If the geographic north is actually a magnetic south, why on earth did we name the compass tip the North Pole in the first place? It's really a south-seeking pole then, no?
It's actually a north-seeking pole, and the reason for the name is purely a historical accident. You see, early navigators, they just named the tip that points towards the north as the north-seeking pole. They didn't know about the true polarity of what it was being attracted to.
So they named it after the direction, not the physics.
Precisely. It is one of those quirks of physics history that still trips up students today. But this whole confusion about poles and the fact that we seem to only ever find them in pairs links directly to a very fundamental law, Gauss's law for magnetism. We need to unpack how these fields work and why they are so profoundly different from electric fields.
Okay, so let's jump into the core concept. At its heart, Gauss's law for magnetism is the mathematical way of stating one simple, foundational idea. Magnetic field lines never, ever start or end.
They never start or end. So if the field lines are continuous, does that mean that magnetic poles, the north and the south, they can't exist in isolation?
Exactly.
Because if I could, isolate a single north pole, that would become a starting point for a field line, wouldn't it?
That is the entire essence of the law. You've hit the nail on the head. You cannot isolate a magnetic pole. It's a so-called magnetic monopole in nature. Unlike with electric charge, where you have isolated positive and negative charges, magnetic poles always come as an inseparable dipole pair.
A dipole, okay. Which means magnetic field lines must fundamentally form continuous closed loops. To really understand this, let's use an analogy. Think of water circulation in a closed pipe system, like for a building's heating. Imagine a pump that's pushing water through a circuit. The water flows from the pump through all the radiators, and then it must eventually loop all the way back to the pump.
Right, the flow is conserved. Whatever amount of water goes into the system must come out in return. There isn't a tap where the water just disappears, or a source that's creating new water in the middle of the circuit.
Exactly that. Magnetic field lines are just like that water flow. They circulate in these perfect closed loops. There is no source, which would be a north metal pole, and there is no sink, which would be a south metal pole. The field lines are conserved. They never break. They never terminate.
Okay, if the field lines are always closed loops, then what happens if I take a bar magnet and actually try to break it to isolate the North Pole? I've always wondered about that.
That is an excellent question, and it serves as the ultimate physical proof of this law. So, if you cut a bar magnet in half, it doesn't matter how you cut it, crosswise or lengthwise, you do not get an isolated North Pole and an isolated South Pole.
So what do you get?
You instantly create two new, smaller magnets, and each of those new magnets has its own North and South Pole.
Wow.
This inherent impossibility of separating the poles shows that this closed-loop nature is fundamental to the very structure of magnetism. The field lines they reorganize themselves to maintain those loops, even in the tiniest fragment.
That makes the idea much more concrete. But scientifically, what was the insight? What led physicists like Maxwell to realize that this observation must be formalized into a universal law? Why is it so crucial?
Very good question. Because the absence of monopoles isn't just a lab observation, it's a profound constraint on the mathematical structure of our universe. Maxwell realized that for electromagnetism to be a complete theory, and this is crucial, for light to even exist as a traveling wave, the magnetic field must be, in mathematical terms, divergence-free.
Divergence-free. What does that mean in simple words?
In simple words, it just means that at any point in space, field lines are not spraying out from it or collapsing into it. They must just pass through. This requirement that every magnetic field must obey this zero divergence rule. It connected all of electromagnetism. For a mental image, just picture an imaginary closed surface, say a spherical balloon floating in a magnetic field. Since the field lines are these perfect closed loops, any line that pierces the balloon inwards must eventually pierce it outwards somewhere else on the surface to complete its loop.
So that the number of in arrows must always equal the number of out arrows. If I count the net effect across the entire surface, it has to cancel out completely.
Precisely. The net magnetic flux through that closed surface is always zero. And that right there is the conceptual basis for Gauss's law for magnetism. Now let's get a bit more formal and see how NSERT defines this law. This is essential for your theoretical understanding and for your exams. Could you read the definition for us?
Okay. The NSERT sort defines the law as the net magnetic flux through any closed surface is zero. Mathematically, CB equals zero everywhere.
Excellent. The entire power of this law is contained in that simple zero on the right side. Let's unpack that by comparing it to the electric version of Gauss's law, which you studied back in Unit 1.
Okay.
You'll recall the equation for electric flux. It's E is S equals Q enclosed U. Now that right side exists because electric charge, the Q, is the physical source of the electric field. Electric field lines start on positive charges and end on negative ones.
Right, so if I enclose a positive charge inside my imaginary surface, I get a net positive flux because all the E field lines are leaving the surface.
Correct. The flux is non-zero because sources and sinks of the field exist. Now look at the magnetic formula again. The right side is zero. This zero is the entire story of magnetism. It fundamentally states that there is no magnetic charge, no QM enclosed, ever.
So the zero basically means that the universe has this profound asymmetry. It allows isolated sources for electric fields charges, but it mandates that magnetic fields must be source-free, always looping back on themselves.
That is the key insight. That zero flux condition is the reason electric and magnetic fields behave so differently. It dictates that magnetic fields are solenoidal, which is just the fancy mathematical term for closed loops. Let's try a quick concept first example to make this concrete. Imagine we take a complex magnetic device, maybe a solenoid or a bar magnet, and we place it entirely inside a perfect closed spherical chamber.
Okay.
If we were to measure the magnetic flux across the entire closed surface of that chamber, what must the result be? It doesn't matter how strong the magnet inside is.
Well, since the chamber is a closed surface, and we know there are no magnetic monopoles inside, the net magnetic flux must be exactly zero, according to Gauss's law. Any flux that leaves the surface must be balanced by an equal amount of flux entering it somewhere else.
Fantastic. The formula EB in RUB is a geometric guarantee that this balancing act will always occur. It is the mathematical formalization of the pattern you see with any magnet. And this concept, understanding that fields are closed loops and therefore divergence-free, is a crucial stepping stone. It's actually one of the 4 key Maxwell's equations that bring together all of electromagnetism, showing how electricity, magnetism, and light are all fundamentally interconnected. Hope everything is clear so far. This concept explainer is from ProfSam.com, that is ProfSam.com. Now let's discuss the silent killers. These are the tricky conceptual points that frequently confuse students and unfortunately cost marks in theory papers and MCQs. We've already talked about misconception 1, which is treating magnetic poles like electric charges. Remember, break a magnet, you just get smaller magnets, not separate poles. But let's focus on a major error regarding the field lines themselves.
How's that one?
Misconception 2. Students very commonly assume that magnetic field lines inside a bar magnet run from north to south, just like they do outside. It seems logical, no, because outside they emerge from the North Pole and curve around to enter the South Pole.
Yes, that seems intuitive.
But it's wrong. To complete the closed loop, the field line must continue from the South Pole back to the North Pole inside the magnet itself. If the line just stopped at the surface, it would violate Gauss's law.
Oh, so the correct rule is, outside the magnet, the field runs from north to south, but crucially, inside the magnet, it runs from south to north. That is very counterintuitive, but I see now that it's necessary to close the loop.
Exactly. Inside is S to N. Outside is N to S. That internal pathway is absolutely mandatory to satisfy the law. You must note that carefully. Now for misconception 3. Some students believe that Gauss's law for magnetism only applies, outside the material in a vacuum, or maybe only when dealing with fields created by currents. This is completely wrong. Gauss's law for magnetism is a universal constraint. The zero divergence rule, AOB, always zero, holds true everywhere. It applies inside materials, outside materials, and even deep inside the core of the bar magnet itself.
So if I were to draw a tiny imaginary Gaussian surface right in the middle of a ferromagnetic bar, the net flux through that tiny surface would also be zero.
Absolutely zero. The law is fundamental to the very nature of the B field, irrespective of the medium or the source. It is a universal rule that every magnetic field in existence must obey. Understanding this global nature, it gives you a much stronger command over the concept. Now, let's lock this knowledge in with some memory anchors just to ensure these concepts stick with you permanently, especially in the high-pressure environment of an examination.
Okay, that'd be helpful.
For the mathematical formula, let's use a very simple mnemonic. B closed equals zero. The magnetic field B is always topologically closed, which directly gives you the zero flux result. Simple.
B closed equals zero. Okay, I can remember that.
For a catchy phrase to anchor the physics, always say to yourself, magnetic field lines are like continuous loops. They never terminate, they never break. This really emphasizes the key physical consequence of the law.
No monopoles means no breaks in the line.
Perfect. And finally, a physical gesture to internalize the topology of the field lines. Use your right hand, curl your fingers to represent the field lines, exiting the North Pole, looping back, and entering the South Pole externally.
Okay, curling my fingers.
Then, trace the path with your index finger through your palm from south to north to complete the loop internally. This small gesture instantly reminds you of that S to N direction inside the material and the continuous closed nature of the entire field. So, to summarize this entire deep dive, here are 3 exam-safe factual points about Gauss's law for magnetism that you must carry into the exam hall for maximum marks. First, the net magnetic flux, phi, through any closed surface is fundamentally zero. Second, this law is the direct consequence of the physical observation that magnetic monopoles, that is, isolated north or south poles, do not exist in nature. And third, magnetic field lines are always continuous. They form closed solenoidal loops running internally from the South Pole to the North Pole to maintain that continuity. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit profsam.com.
That is PROFSAM, right?
Yes, PROFSAM.com. We really hope this deep dive into Gauss's law was helpful. Keep practicing these conceptual comparisons and you will find electromagnetism becomes much simpler. Good luck with your preparation.